Hello everyone. Today we're going to compare PyMc Marketing, the Python open source library for marketing mix modeling that uses Bayesian statistics, versus Cassandra, the MMM software for non-technical marketers that guides media allocations decisions to optimize media ROI. We're going to evaluate these two methodologies based on accuracy metrics, ease of use, actionability of the insights, and overall utility generated for the company. So stick with me. We're going to dive into both of them. First thing first, we're going to see what is the data that we're going to use. Here we have the dataset. It's an extremely simple dataset in which we have the first column represents the data at a weekly basis. We have revenue at a weekly basis. And then we have a list of medias plus some organic variables. So first we have TV spend, TV media, out of home, print, Facebook, and search. And these represent our media factors. On top of that, we have one organic factor that is newsletters. And then we have a context factor, which is events. Everything is aggregated at a weekly basis. And it has between, I think, 4 years of data. Between 2015 to 2018 is going to be enough in order to train our model. Keep in mind that best practice is to have at least 10 rows per each variable that we're going to use in our marketing mix model, which means that if we're going to use 1, 2, 3, 4, 5, 6, 7 variables, we need to have at least 60 rows. If each row represents 1 week, which means that we need to have at least 1.5 years of historical data. Now, let's dive into the PyMc Marketing library. But before I do, in the description here, you're going to see this file that you can copy and paste. You can go here, File, create a copy, which is a data request checklist for Cassandra's marketing mix modeling. So let's dive into the PyMc Marketing. Let's start with that, and then we're diving into Cassandra's. So first thing first. What we want to do as a first step is obviously install PyMc Marketing. So pip install PyMc Marketing, and the training starts. What I want to start after installing PyMc Marketing is to add some warnings, just in case if anything happens. I want to know any bug happens. I want to know why it happens. So let's run this cell. What we want to import right next to it is pandas, numpy, matplotlib, seaborn. These two are for graphs. Then we want to install rvis as AZ. We have PyMc as PM. This is not strictly necessary, but I imported anyway. If something in PyMc Marketing doesn't work, I can actually use the original library, which is PyMc. And then we are going to install and download all the variables and all the functions of PyMc Marketing. PyMc Marketing, by the way, is a really new open source library developed by an amazing team. In the past week, I've studied the entire open source library. I'm not an expert about this library, but I'll try to show you in the simplest way possible how you can leverage it in order to generate utility for your company. So we download all the functions from this open source library, and then we want to actually download the max upscaler and min max scaler that we're going to use in our training phase and in order to standardize our data. So let's run this. Awesome, we've imported all the requirements. The SNS set theme is just a way to set the grid for our graph, so I'm just going to run it. It's really easy. It's not a requirement. First thing first, what I want to do is I want to upload my CSV file. So let's go here. Let's Cassandra data request checklist example. I'll upload it here. And what I'm going to do is copy path, and I'm going to paste it here. The first thing I do is I import using pandas the CSV file. Then I replace any infinite value that I might have in my dataset. Then I fill all the NA with 0. So if I have any NA value or any cell in my dataset has a none value or an infinite value, is first transformed into none, and then from none to 0. Then I check if I have any none values, and I print. Obviously, I want to know if there is still any none values after these operations. This phase is extremely important in order to validate manually if the dataset that we have has some errors inside, it requires our data cleaning operations. So I'm going to run this. it looks like that we have no none values in our dataset, and we've imported everything smoothly. So we're going to create and export the list of the columns names that we have in our dataset to simplify how we're going to fill the form of identifying what are the variables, what are the output variables, etc. So let's run the F columns. We have a list of our variables. And now let's define the output variable as revenue, the date variable as date week, as we can see. Here we have a script that allows us to identify and create a list of strings that represents the names of the media variables that have span inside of their label. Now, as you can see here, we have TV span, out of home, print, etc. And they're automatically included into media. And then we have context variables, which are events and newsletters. With PyMc, fairly sure that we don't have organic variables feature that we can identify. So everything else that is not media is identified as a context variable. So let's print media and then see if it works. Awesome. We've imported all the variables automatically with one click. Now, I've used ChatGPT in order to create the script for building a seasonality. So I want to extract from the patterns of my sales what's the seasonality of my business, or the business that we're going to model. And it works in this way. So function called extract all seasonality. We need to define what is the data frame, what type of seasonalities we want, and what's the window size. So how many records represent 1 month. And what we do, this is the function. We can copy and paste it. So we run it. Awesome. We've run the function. We can call it now. Now, what we want to do in this cell is first, identify what are the seasonality features. These seasonality features need to be the output variable and the date variable. I want to print them just to be sure that I did the right job. And then what happens here is seasonal df, which is a data set composed by only the variables that are going to help me understand what's the seasonality. So it's going to be df, which is our data frame with our 2 columns, and I'm going to copy it. I'm going to add a new column that is going to be called ds. And ds is a normal label name to identify dates into a data set when you use profit or you use, in this case, this function. We're going to rename revenue with y, just to standardize. And we're going to identify that the seasonal configurations here are the period, the quarterly period has 12 weeks inside, and the yearly period has 52 weeks inside. In order to simplify and identify how you need to model the seasonality here, you need to identify these 2 parts. It might seem a little complicated at the beginning, but believe me, when you get used to it, it becomes really easy. So the last thing that we do is we insert everything inside a variable, extract season, so we create a new dataset mainly, and we run the function extract for the seasonality, defining what is the data frame that we're going to use, the configurations of our seasonalities, and what's our window size. So I'm going to run this cell. I have the right columns. I have the seasonality. If I want to check if there is any graph that we can run from this, right? What interests me is this one. This is the graph that represents my multiplicative seasonality. So how the demand changes over the year, over time. And it looks like there is a pattern that repeats itself over time. Now, let's print this in an actual graph. This function in this cell just works in order to simplify and show you all the parts of the quarterly seasonality and the yearly seasonality. So let's run this. Awesome. So as you can see here, there is a pattern that repeats itself quarterly and a pattern that repeats itself yearly. We want to import these 2 inside of our actual data set and add the quarterly and yearly variable inside of our modeling experience. So what we're going to do, first of all, we're going to split, create a variable that's called weeks to split. Separate the test group, the test data frame with the train data frame. And we're going to split by 4 weeks. So we're going to leave the last 4 weeks as a data set, as a data points that are not going to be used in order to train our model. We need to identify, we need to add a new column called df quarterly. and we're going to insert the values that are in extracted season quarterly. Same thing for yearly. And what we did, basically, we added in this part 2 columns that are going to be then used in order to train our model and added as context variables. Let's recheck and substitute all the infinite values into nones and from none values into zeros. We don't want any none value, or the modeling procedure and the training does not work. Then what we want to do is we want to separate the data frame for training and the data set for testing. And then what we want, and that's it. So let's run this cell. Awesome. So in here, what we are to do is we want to create, first of all, the context variable list. I'm going to add from context the 2 new columns that we added into our dataset. Second thing that we do is we call MMM, our object that has the function inside called delayed saturated MMM. This delayed saturated MMM is going to use add stock and diminishing returns inside of the training procedure in order to find the optimal add stock, the optimal diminishing returns. And we need to define first, what is the data frame that we're going to use? What is the target column? And we did. What is the date column? Here we did. Channel columns, we created a list inside of media. Control columns is a list of strings that we actually did here. The add stock max lag, which is how many lag effect there can be at a maximum in our dataset. And 8 is really wide. It means that there can be a 2-month lag effect, which is crazy. But we're going to keep it like this. And we want to have early seasonality. We want to model the early seasonality and consider the last 2 years. So we're going to run this. Awesome, it worked. We're going to rename X and epsilon just to simplify our training procedure. And we're going to add into X all the values that are not the Apple variable or dates. And Y, we're going to define only the Apple variable. So we're going to run this. Awesome. And then we start the training procedure of our MMM. Now, this MMM is not really complex. I know it. I tried to model it before, and it's not really complicated. It's really easy. There is no multicollinearity. There is consistency on the data. There are enough records on each variable. So I'm not going to complicate it too much. I'm going to use x epsilon mmm.fit x epsilon, just simple. Target accept is the statistical significance of each coefficient that is going to come out. Number of chains, so how many iterations it needs to do, and how many tests and experiments and draws needs to do in order to train it, in order to tune it. So I'm going to run this cell, and it's going to take around 20 minutes, more or less, in order to finish. So I'm going to leave it train. In a little second, we're going to see a bar plot that actually loads over time. It started loading here. It's going to take some time in order to load here. While it trains, let's go and use Cassandra in order to train our model. Because any training is going to take some time. So let's go inside and see how it works. So we are inside of Cassandra. The first thing that we want to do is we want to add model. I want to use my own data set. And I'm going to drag and drop our CSV file. Awesome. So we've added our CSV file. We click next. And in this case, we need to do the same thing that we did previously. We need to fill the form just to tell the model what each column represents. So let's call it YouTube. Date column, which is date week. The output variable type is revenue. The KPI is revenue that we're going to model as an output variable. The media channels are these ones are already selected. Paid media, organic, and contextual. Let's define the country. Let's use United States, I think. And now, what we need to do now in this experiment is just to click next. That's it. Everything looks correct. Let's continue to the modeling procedure. So here, what we have here is an EDA analysis already done for us that actually shows us the pattern of each variable over time. We identifies if there are some warnings. And these warnings in this case are TP, out of unprinted search have low spam volumes. And this is interesting. So I did not know that. I thought I was using a dataset that actually was working with no problems, but it looks like there are some problems. In fact, if we hide all channels and we check only on Facebook, compare it with TV, we see that the dimension of this data is completely off. This is probably because there is a problem with the dataset that we need to check. So let's go back to our dataset here. And it looks like that we're taking 72 million per week is a little too much. What I did wrong probably is Facebook spend one is I formatted wrongly this data. So what I'm going to do is I'm going to divide this by 1,000, not 10,000, but 1,000. And this is the actual value. I did this mistake. I did not expect that. But thanks to Cassandra, I actually could check this before starting the training. Now, going to go back here, going to download the dataset, we upload it here. Awesome. Click next, fill the form again, YouTube, define this is revenue. Let's call United States in order to get the holidays from this particular country and model the seasonality with it. Click next, receive back the EDA analysis again. Now everything looks more concrete and with the same dimension. We see the revenue over time versus the spend over time. We see all the other variables here. We want to create a model now. We click create model and the modeling procedure actually is done. The only thing that we need to do is click train model and the training starts. So it's a 3-step procedure in order to train your MMM. All right, training started. We click OK. We check the status. Okay, training is starting right now. If it says it's not started yet, we need to wait for a couple of minutes. We refresh it and we check status. Okay, not yet, but it's going to start really soon. So we need to go back to our PyMc Marketing training because we noticed wrongly that our dataset is wrong. So we're going back to our PyMc. Yes, it finished the training, but we need to retrain it again. So going to delete the old datasets that we added here. 1, 2, and 3. Let's add the new dataset, copy the path, and add it again on top of it. We need to rerun everything. So really quick, nothing is too heavy. Everything is really easy to do. And now it should start the MMM fit really soon. It's going to take a couple, I think around 10 minutes in order to finish training. Awesome. It took around 10 minutes in order to train this model. Here we have some posterior analysis, which are extremely hard to translate into rational values. So this is why we're going to use graphs in order to explain all the information that we can derive from this MMM. So first thing first, let's create component figs mmm.plot components contribution. The cool thing about PyMc is that it is really easy to create plots with the outputs and derive what is the accuracy, what are the actionable insights that we can implement. So let's run this. Awesome. So in here we see the contribution that I have. Everything is scaled down with the min-max scaler that we use. But we can see that there is 40% of the contribution is explained by the intercept. Then we have some other variables. The medias have between 0 and 20% of contribution. And then the seasonality has about plus 20, minus 20 contribution in our media mix. This is really interesting. And it's a cool thing to summarize all the variables that represent media, represent control, and the seasonality contribution in this way. Because it simplifies and actually shows you some macro insights that we can derive from the first training that we do. So after that, what we want to do here is we want to get a contribution of each factor. So how each factor contributed to generate sales and how many sales are coming from TV, out of home, Facebook, etc. So let's run this. We created a data set in order to see what is the contribution of each factor. And then what we want to do, I'm not going to spoil you with the diminishing returns curve, but we want to get the diminishing return insights. So we want to see what's the contribution of each factor based on the volume of investment that we have. And the cool thing about PyMc is that we can have the confidence interval. So we can have range that represents the probability of the 95% probability of having that specific output if we spend X, for example. Everything is scaled down scale down here. This is the contribution, and this is the shape of the curve. If we want to see out of home, for example, same thing here. We see that if we invest 400K, we get around 150K of revenue. So ROI is really low here. Let's see if we have something with Facebook. With Facebook, if we invest 75K, we get 100K of contribution. This is interesting. It looks like in this MMM, this channel works really well, but the value can be between 25K of contribution if we spend around here, up to 200K of contribution. It's really important to understand that any statistical analysis that we do needs to have some idea of confidence interval. The idea of confidence interval just shows you what is the level of uncertainty that each measurement has. And having that into each specific graph that we run is extremely helpful in order to calibrate our decision making on top of these insights. Awesome about this. So we see in here, if we invest 100K, we get a little less than 100K of contribution out of really strange values, really big values. It's really interesting. I think this one summarizes, yes, this graph that we're running summarizes everything into one plot, so we can compare them. We can compare each graph simultaneously. So we can see that TV spend has the highest contribution based on the X factor, which is how much we invest, and there are other values that we can explore manually. But what I want to show you step by step is, first, what are the insights that we can unlock? And then we evaluate the results, comparing the results with the MMM built by Cassandra. Let's run MMM predict posterior. In this way, we're running the MMM, our object that we've trained, and we use the function predict posterior, and we import the X in order to predict the output variables based on the input variables that we have historically. And then what we need to do is just plot posterior. Awesome. All right. It looks like it is pretty accurate. There are some moments that forgot. As you can see here, you have dark blue what actually happened to the sales, and in light blue, we have some, there is the confidence interval. And on average, it looks like it is really accurate. But what I want to do is I want to print the R-square and the MAPE, which are two accuracy metrics that we use in order to validate what's the level of accuracy of our MMM. Now, the R-square, I have these scikit-learn R2 score and mean absolute error function that are used to actually derive these values. The R-square actually is not really an accuracy metric. It's more like it actually tells you how many variations in the output variables are described by the variations in the input variables. Then we have the MAPE, which is the percentage error that we actually see on average. And in this case, we have an 86% R-square and a 10% MAPE, which is interesting, really, really interesting. It's not bad. On average, you start leveraging and using the MMM insights when the accuracy level, the R-squared level, is above 80%. The MAPE is a little big, but we can still use it, definitely. What I want to do is I want to scale up everything at an original scale. Awesome. And now we want to plot the contribution of each factor. So we want to see over time what were the factors that actually contributed to generating revenue. Now, there is this function. I don't love it because it's called plot grouped contribution breakdown over time. I don't love it because it uses matplotlib. I have some problems into running it every time, and it shows you just a small picture that we cannot filter the values inside. So as you can see here, there is a big impact on a certain value here, the yellow one. I don't really know what it means. Probably I've scripted the function without including the labels of each color. My fault. But I find it a little complicated in order to derive the real contribution. Because what I would like to have is filter each factor if I want, and identify and analyze each one by one in order to simplify my analysis. And if ideally, I would like to compare these insights, these contribution insights over time, to the spend level that I had historically, in order to understand whether at certain points we've overspent or underspent in each specific channel. Now, I'm not going to, let's run these plot channel parameters. I want to see the alpha. I'm not going to include a lot of insights about this because it's a little too technical. I don't want to overwhelm you about this. This one is the same. Let's create though. For each variable, I want to see what's the ROI measured. In here, what we have here is channel contribution scale. We compute the channel contribution at the original scale again. We create and we analyze for each media that we have in our media mix, the ROAS. And as you can see here, it shows us not only a deterministic output, but also the probability distribution of the ROAS of each channel. And this is amazing, I would say. Any marketer, even though this is extremely difficult to understand at the beginning, but any measurement that we do based on our data, it always has a probability distribution. A confidence interval is a list of values that have 95% probability of being true. And as you can see here, this probability distribution has a lot of values. So there is this violet value. I need to print the labels here, but it looks like this violet value can have a ROAS between 3 and 0, while there is this blue one. It is concentrated between 0.5 and 1. This is really interesting. And this green one has a really wide distribution like this red one. Now, awesome insight so far. What I want to do, I want to go to Cassandra and see if it's done training the model. So in here we have the new model that we've trained. Let's see the results. So differently to PyMc, what we receive as an output from the training is a list of models that are actually really similar here with a certain accuracy. And all of them are ranked by lower rank to the highest rank. And here we have the best. The reason why this is the best is because we actually try to understand what's the level of uncertainty, the accuracy, and the average error this model has. Now, compared to the model that we've trained with PyMc, we have 95% accuracy with respect of 86% and 5.99% error compared to 10% error. Now, obviously, I remind you guys that this is not, these are square, which is the percentage of the variations in the input variable described by the output variable described by the input variables. Now, as we can see, we have the data set. We see that it is really accurate on average. We see that, we have 28% contribution from the baseline, while we saw previously that the baseline for the model with PyMc was 40%. Search contributed for 24%, TV 23%. What I want to see here is the ROI of each campaign type. Oh, this is interesting. Wow. The ROI measured according to this model are way higher than the one trained with the PyMc. Obviously, PyMc has a higher baseline. So what we're seeing here is that a big percentage of the baseline is not attributed to the baseline, but is attributed to the revenue and to the input, the media variables. And the confidence interval are pretty consistent. The lowest ROI channel is print that can have an ROI between 2.7 and 7.9. Out of them can have between 4.47 up to 10.16. And this is really interesting. So let's go back to the distribution. Here we had the ROAS split by each campaign type that went from 0 to 3. Let's actually, oh, this is my bad. Let's expand this to 10, right? Right, so the ROAS went from 0 to 4, not to 3. But the ROAS are really, really different. This is actually really interesting. And here we can see the contribution of each factor over time, and we can see the ad stock. I didn't find a way to export the ad stock from the MMM object that we trained. We can actually run an additional function, which is dir open parenthesis MMM. So we can actually see what are all the function that we can call from this object. Ad stock max lag, but it's 8 is the one that we inputted. I cannot see any function to actually print or show me what's the ad stock effect and actually see it into a graph so I can understand how to interpret it. But then, right, so let's use this data set, this model. I'll save it and let's dive into all the insights that we can derive from it. So we go to models overview. Let's select our YouTube model. Ooh, we have some suggestions. So it created some suggestions for our media mix, and these suggestions are appeared here. And they tell us, right, it says that Google search can generate even more revenue if it increases weekly budget to this volume of investment. Well, Facebook is not performing as good as other channels in your media mix, so we should reduce its weekly budget down to this volume. This is interesting. I mean, it's implemented here just to show you a simplified interpretation of the insights. Because most of the times, if you are an analyst, you need to explain each graph to each marketing stakeholder. And if you need to repeat this for every meeting, it becomes extremely expensive operational-wise. So this is why next to each graph there is an explanation in natural language that explains what this graph means and what to do about it in order to optimize your media mix. Now, we saw the confidence intervals. There are between 3 and 10, which are bigger than the PyMc. The contribution, the baseline is lower here compared to PyMc. Seasonality is actually similar. In here we have a window of 1 year from 1st of January to December, but the pattern is really similar to the one that we saw previously with the PyMc. What I want to do is I want to check for each campaign type and the contribution that they had over time. I want to see how much each factor that I inserted in my model contributed to generating revenue. So let's say we want to see just Facebook, and this is the contribution of Facebook. We see that Facebook generates weekly between 149K and 103K, more or less. This is the range. This is interesting. I want to see the baseline contribution. The baseline is around 500K per week. Let's add seasonality to it. And thanks to seasonality, we can actually see the variations over time. And it makes sense because during the end of the year, we have a positive spike. What I want to see is the contribution of TV. The contribution of newsletters is really minimal. We add out of home, okay, and then we add the holidays. There is one thing that it looks like that events have a huge effect here. Yes, they were the reason why there is a positive spike during the 22nd of April. So we go back to models overview. In the models overview, here, these spikes are explained by the event. I want to see not only the contribution, but also the ROI over time. So there were moments in which the ROI of out-of-home was 214, which is crazy. And there is another moment in which TV ROI was really high. Now, this is really interesting. I want to know what happened in those cases. So I'll hide this channel. I just check TV. And this is the 2nd of September. In here, we have the spend over time of each factor. Let's select only TV. So here we have 2nd of September. 2nd of September, we spent 0, but we had some ad stock effect, which means that we can see it here. So hide channels, here we see. 2nd of September, we've spent 0, but we've had some ad stock effect generate as a carryover effect, generating revenue for us. And this is why we got this spike in ROI during that moment. I want to see not TV, not out of home, but only Facebook over time. It's pretty consistent. On average, we have 3.5 to 7. Print, consistent with Facebook. Out of home has this positive spike, but then it's consistent. And then search. Search has a really nice distribution, around 8 ROI. Let's see which channel is covering the diminishing returns. And what I want to do now is I want to compare the diminishing returns found from Facebook with the ones from PyMc. So let's go back to our diminishing returns. All right. So let's select Facebook. 100K represents 150, more or less, right? 100K of spend represents 381K of revenue. So this is interesting. Now, this shows you the mean, right? So this is how much revenue is attributed to Facebook per each volume of investment. But the ROI and the contribution can go up to 250K of contribution in terms of revenue for 100K of investments. It is still underestimating compared to the model built from Cassandra. Is any other stock effect? Print has a delayed effect. This is interesting. The delayed effect shows us what's the lag effect between the moment in which we invest and the moment in which we see the maximum impact coming from the previous investment. And shows you what's the carryover effect. So for how long will I continue generating revenue, even if I shut down my campaigns coming from that particular campaign type? Skip this. So as we saw, we have pretty big differences in the ROAS/ROI measurements between the PyMc marketing. It is highly underrating these media channels contribution versus the contribution measured by Cassandra's. Now, I'm creating an assumption here. I'm not an expert. If you have a better interpretation on why this phenomenon happens with the same data, please share it in the comments below. But I think that there is a different way on how we handle ad stock for this specific PyMc marketing library. So this is why we see a different ROAS. The easiest way in order to understand what's the true incremental contribution right now, it would be to run an prescient-ai test, probably on the highest spend variable, which should be, according to this model, the highest spenders are TV and search. So I would run an prescient-ai test on search in order to validate its real incremental contribution. Now, going back here, what I want to leverage now is the ability of having an open source library that we can play however we want. So we can actually see what's the accuracy in R-square and MMM for test data. At the beginning of this video, we split our dataset in two groups, and we've trained our MMM with the first training data, and now we want to see how well it can predict the future. But what I want to focus on is I want to first print all the columns. I want to be sure that the F-test and the F-trains have the same columns. And then here we run the script in which we don't need this, but we define X-test as a DF test, as we did before, Y-test the same way. Then we print the shape just to be sure that the shape is consistent with what we want to predict. Y-pred, which is MMM.predict X-test. In this way, we predict the mean values that we're going to receive. I'm going to insert everything into Y-true. We get Y-true, which is the same thing as Y-test, the actual sales that we generated, and we compare them in order to measure the R-square, as we did previously. If we run this, we get the R-square on non-trained data is 40%, and the map is 6.2. So the error is lower, but the R-square is lower, which is not a problem by itself. We have only 4 data points, which means that not all the variations in the output variables are well described by the variations in the input variable. I want to run this script again because I want to see why we got it so low R-square. And the reason why is that in this point and in this point, it didn't quite get the incremental value. And the reason why it didn't quite get here, it overestimated sales, and here it underestimated sales. I assume because in here, we did not take into account the actual lag effect that the ad stock of previous investment had on the media mix. And in here, it's probably because the ad stock that we actually generated is not big enough in order to bring the carryover effect over time. I'm having a hard time in order to understand how to derive the ad stock effects from this training model, and this obviously influences the accuracy. This, though, doesn't mean it is a wrong model. It means that I'm not able to extract what are the upper parameters for ad stock for this specific library, but it means that it can still be used in order to optimize the distribution of our budget. So let's do an example, right? So I want to do here, I want to run a budget allocation simulations, and I want this budget, I want this model, and tell me exactly how I should distribute my marketing budget week over week. Now, it's not really flexible. The first thing that we need to do is we need to retrieve the diminishing returns hyperparameters with this function. So I'm going to run this, and then I'm going to use the sigmoid parameters. I'm going to insert it inside of this function, which is optimize channel budget for maximum contribution. I'm going to use the sigmoid methodology, which is just the shape and the function for the diminishing returns curve. I'm going to insert the marketing budget that I'm going to invest, and the other parameters, which are these ones. I'm going to run this 208K for the next week of marketing investment. I'm going to run this. And what I see is a new distribution, a new estimated contribution split by each campaign type. And here we have the total. So the total is we're going to invest 2.08 times 10 to the power of 5, and here 225 times 10 to the power of 5, which means that we're going to have an ROI or a ROAS of 1.1. Take into account this. When you use this budget allocator, it only suggests you the optimal distribution, not taking into account the ad stock other parameters and the ad stock effect of previous investments that we had in our marketing mix. So according to this simulation, we're going to have 1.1 marketing ROI. Let's try with Cassandra. So with Cassandra, we have a little bit more flexibility. So we go to optimize budget. I'm going to click new budget allocation. Let's predict the next week, right? If we do tests, I want to predict week 208K. I want to this is 2018, 11, 18. So going to do this, want to predict only the next week of marketing budget. Let's click optimize budget. Now, if we invest 208K, we're going to generate an optimal ROI of 9.92, which is 35% more than the previous week, which is completely different from what we saw in the other library. The reason why is that we take into account all the historical data and all the historical ad stock that there might be into this simulation. So what we do here is we bring the ad stock of previous investments till to the last data point that we have, and we forecast it. And if you work a lot with MMM, you're going to see that ad stock has a really big effect over time, because it compounds the effect over time. Now, according to this simulation, we need to invest less almost on everything, but especially focusing on a lot less money allocated to search, a lot less on Facebook, almost half on print, and a little less on TV. Let's compare these two results with PyMc. Let's see how much it suggests to invest on Facebook versus out of home, print, etc. So on Facebook, it suggests to invest 5.61. So 56K on Facebook versus Cassandra tells us to invest 84K. Then to invest in out of home, I think a lot. Actually, this is actually here. No, sorry. Here it suggests us to lower the marketing budget by a lot. So it's 5.61 to the times 10 to the powers of minus 10, which is, we don't need to spend anything here and anything here, I guess. And then we need to spend a lot of budget on print. So 6.39 to times 10 to the power of 4 should be 63,000. In here, we suggest to invest 14,000, right? In here, we need to invest 56,000. Sorry, here is 63,000 on print, 56,000 on search, and 87,000 on Facebook. So on search here, it says 95K versus the 56K that's suggested on search. On Facebook, we should spend 87,000, and we suggest to invest 84,000, fairly similar. And we should not spend anything on TV, out of home, and out of home. But we're spending here some on TV and zero on out of home. So these are the two comparisons. What we can do with Cassandra automatically is we can implement these suggestions, and then we can refresh the model after 1 month, right? We refresh the model, and every time we refresh it, we can compare the actual contribution of media factors versus the factors that versus the prediction that the budget allocator gave us. But we can do the same thing with PyMc for sure. It's a little more manual. Now, we've got a lot of information sold together. I'm sorry that I'm not extremely expert about this topic, about this particular library. It only took me 1 week of training in order to get to this output. What I can say is that we can evaluate PyMc Marketing as a really robust open source library that someone can use fairly easy. I mean, it took me 1 week to understand how it works. That probably is going to take you a shorter amount of time if you follow it to this point. It's a tool not specifically for data scientists that understand how Bayesian statistics and probability work. So I would say is to use 5 out of 10 because we compare it to a SaaS no-code product. Flexibility, I would say 8 or 9 out of 10. It's extremely flexible. There are a lot more other parameters and priors that we can use in order to model and change the posteriors that we get from these trainings. Complexity is 6 out of 10, and granularity and the utility that it can bring to a company, I think it's a 9 out of 10. The cool thing about this is that it embeds the probability distribution on every measurement that we do. So it is extremely, extremely powerful. I would suggest PyMc for all the companies that do need to create a really robust model for their brand. They have a data scientist team, a data engineering team that can actually run these analysis week over week, a month over month. It is it's not super cheap because it requires all the people, but it's a free open source library that you can actually start to use and learn really, really quick. To be honest, it's the easiest open source library with the right insights about probability distribution and taking into account uncertainty level that I've ever seen so far. Compare, Cassandra is 9 out of 10 ease. I mean, it takes 3 clicks in order to create an output. It's really easy to refresh, so easy to use, 9 out of 10. Utility for the business, I would say 7 out of 10. I mean, it generates pretty cool insights that are really easy to interpret and validate over time. One thing that is not super on point is with these probability distributions. I mean, we use an evolutionary method, not a Bayesian methodology, in order to measure the uncertainty rate of the MMM. It's just two different techniques. But we've optimized our UI and our insights in order to be extremely easy to be interpreted by non-technical marketers. So all the insights then are interpreted through our systems and then explained in natural language, as we saw previously. So I would say PyMc is for companies and brands that have a data science team internally. Cassandra is more suited for non-technical marketers or marketing agencies that want to scale up their measurement operations. Hopefully, this video has been useful for you, and I can't wait to challenge another open source library about MMM. See ya.